Okay, we are now recording. Um, so guys, today is going to be a pretty straightforward day. We're basically going to continue our conversation into waves that we started last time, and I'm going to introduce the speed equation, do a few examples with you guys, and then hopefully you guys will be ready to do the assignment posted. So today shouldn't be too bad of a day, and I'm gonna try not to hold you guys too long. Well, I will not hold you guys that long. Like I said, we got just a little bit we got to do. So if you click on the folder, well, click on today's class and click on this class and then click on the folder for this week. Today is May the 19th, and it is a Thursday. Okay, so you guys notice I have an assignment for you guys to complete called the wave speed assignment. Basically, what we're going to do, we're just going to do some few example problems together, and then you guys should be ready to do this assignment. But before I do that, guys, let us review a few things that we talked about on last time. So remember on last time, I introduced harmonic motion. And remember what I said about harmonic motion. Harmonic motion basically involves any process that repeats itself over and over and over again. If the process is repetitive, um, we say that that physical process is demonstrating harmonic motion. Okay. Now, whenever we're talking about waves, remember waves combine both harmonic motion and linear motion. For example, if you have an ocean wave traveling along, right? So if you have a wind, the wind carrying an ocean wave along, so that wave has a linear component, right? Because it's moving throughout the ocean, and it also has a harmonic component because if you look at the surface, of that wave, you're going to see it's kind of bobbing up and down, up and down. So as it bobs up and down, that process is repetitive. So waves combine harmonic motion and linear motion. Remember, one of the things that we talked about last time, guys, there are two main types of waves you guys need to be aware of. You guys need to be aware of transverse waves, and you guys also need to be aware of longitudinal waves. Okay, so these two types of waves you guys need to be aware of. Remember what a transverse wave is. A transverse wave involves vibrations that move perpendicular to the direction of wave propagation, whereas longitudinal waves involve waves that move parallel to the direction of wave propagation. So, and I showed you guys this last time how, notice here in this video here, we have a slinky. And in this slinky right here, notice how this guy here is producing transverse waves. Let's look at that in slow motion. So let's look at the transverse wave that's created. So that's how a transverse wave looks like. Okay. Now compare that to a longitudinal wave. So a longitudinal wave will look something like this. Okay, so we have a slinky. Notice how he's producing the longitudinal waves. Okay, and of course we're going to see that in slow motion. So look carefully at that longitudinal wave in slow motion. Okay, so everybody see that? In one case, notice how there's energy pulsating from this point to this point of the slinky, right? So the energy is traveling in this direction. But notice how he's pushing his hand forward and backwards, forward and backwards, forward and backwards. In other words, his hand is vibrating in a way that is parallel to the direction that the energy is moving. They're acting in the same direction. Whereas in a transverse wave, the energy, even though the energy was traveling like this, the vibration was happening like this. So in this case, the vibration is happening perpendicular to the direction that the energy is traveling. Okay. Now, guys, let us talk more about longitudinal waves. I want you guys to recognize a real-world example of a longitudinal wave in nature. It turns out, guys, sound sound is an excellent example of a longitudinal wave. Um, in fact, when I'm talking to you guys, as I'm talking right now, I'm creating longitudinal pressure waves in the air around me. So the air particles are vibrating, and that's what causes sound waves. So here's how this works. Imagine here that this right here is a speaker. So imagine you see a speaker that's pulsing. And of course, you guys have seen, like, loudspeakers that have a really high bass pulsing like this. So imagine here this is a speaker that's pulsing. And right here we have several air particles in a room. Okay. And all the way off to the side here, imagine that we have someone's ear. So let me draw ear here. So imagine that we have someone's ear. Let me draw ear. Okay. So here's someone's ear. Okay. So what's going on here, guys? So as the speaker pulses, it sends energy traveling from this end of the room all the way down to that end. So the energy is traveling in this direction. Okay. And so obviously the energy is what's causing these air particles to vibrate. Okay. Now, guys, how do we know this is a longitudinal wave? Because look closely, even though the energy is traveling this way, look closely at one of these air particles. So like, if we focus on one of these air particles here, we can see just looking at only one of those particles, you see how it oscillates to the left and then to the right, and to the left again and to the right. So notice this vibration is occurring parallel to the direction that the energy is traveling. So guys, the reason why you're able to hear guys, the reason why you're able to hear, because basically imagine that you're on this side of the room. What's going on here, these air particles are slamming into your eardrum at a very particular frequency. In fact, they're hitting your eardrum at the precise frequency that the speaker is pulsating at. And so your brain is interpreting those changes in frequency as sound. Okay. So that's how sound works. Okay. So guys, if I was in outer space and I was screaming to the top of my, if I was in outer space and I was screaming to the top of my lungs, and you guys were next to me, believe it or not, you guys wouldn't even hear me. You will not hear me because there's no air particles in space. There's no air particles to propagate these sound waves. Okay. So you need air to propagate sound waves. And sound is a form of a longitudinal wave. And of course, here's an example of a transverse wave. So imagine this was a rope here, and we had someone on this end, kind of shaking the rope like this. So as they shake the rope, they produce energy. Basically, they produce energy traveling from this end all the way to that end of the rope. Okay. And if you were to focus on any one particle of the rope, so like for example, like guys, just look at only one of those particles. If you notice, the particle is moving up and down, up and down, up and down. So in this case right here, this is a transverse wave. Because notice how the particles of the medium, they are vibrating perpendicular to the direction that the energy is traveling in. So this is an example of a transverse wave. Guys, what about water waves? What type of waves are water waves? Well, guys, it turns out that water waves are a combination of both longitudinal waves and transverse waves. How do we know that? Because guys, look closely at one of these water molecules here. So notice how, if you look closely at this water molecule, notice how it moves up here and it moves down here. So not only is it moving up and down, it's also moving side to side, right? Because we see it moving to the right here, and we see it moving to the left of here. So this is moving up and down at the same time that's moving side to side. So clearly, this is an example of a combination wave. So water is an example of a combination wave in which we have water is an example of a combination wave in which we have transverse waves and longitudinal waves combined. Okay. All right. So hopefully that makes sense. Okay. Going back to these notes that we talked about last time. So guys, remember the terms that I introduced to you guys last time. I talked about crest and troughs. Remember, crest represents the highest point of your wave. The troughs represent the lowest points of your wave. The amplitude represents the height of the wave as measured from the midpoint. And wavelength represents the length of the wave, or the length of one cycle. You can either measure your wavelength from crest to crest, or you can measure from trough to trough. Okay. Now, with that said, let us get to the meat of what we're going to be talking about today. Today, we're going to be talking about wave speed or wave velocity. Guys, in order to do these problems here, there's a simple equation that you guys to know, and then that's this equation right here. In fact, if I were you, I'll write this equation down because this is the equation you're going to utilize on your assignment for today. Now, guys, whenever you're calculating velocity, is equal to frequency times wavelength. Sometimes, guys, you will see some textbooks write this equation like this. Sometimes you'll see some textbooks write this equation like this. That says the speed of a wave is equal to wavelength times frequency. Right, so mathematically, speed and velocity mean the same thing. So you'll see like this, velocity equals frequency times wavelength, or you'll see it written like this, speed is equal to wavelength times frequency. Again, same thing. They mean the same thing. Okay. And you guys are going to use this equation anytime you're calculating the speed of a wave. Just so we're clear, I want everybody to understand what this symbol right here means. This is right here. This is the Greek symbol lambda. And what lambda stands for wavelengths. So we use that symbol to represent wavelengths, right? So that's the Greek symbol lambda. You guys obviously know what F is. F stands for frequency. And of course, frequency is typically measured in hertz. Wavelength is measured in meters typically. Frequency is typically measured in hertz. Okay. So this is the equation you're going to use to calculate the speed of a wave. Okay. Now, with that said, on last time, we worked out a lot of these problems together. Now, notice I skipped around a little bit last time, but I want to come back to these problems, and I want to do these problems that involve calculations for speed, which is what we're going to do now. Okay, so we're just going to do a few of these, just enough for you guys to get the point. So right here it says a wave has a speed of 2 meters and a frequency of 1.5 hertz. What is its speed? So remember what speed is. The speed of a wave is equal to wavelength times frequency. So if we plug in what we know, so we know wavelength is 2 meters. Here the frequency is 1.5 hertz. We can easily calculate speed here. 2 times 1.5 gives me 3 meters per second for my speed. Okay. So whenever you guys are doing these calculations on your assignment, be sure you get your units right. Okay, so super easy. Let's move on. Right here it says a wave is 8 meters long and has a frequency of 3 hertz. Find its speed. So speed is equal to wavelength times frequency. Okay, so the wavelength is 8 meters. The frequency is 3 hertz. So what is the speed? 8 times 3, that gives me 24 meters per second for my speed. Okay. Super easy. Okay. Let's look at this one right here. It says a wave has a speed of 50 meters per second. If its frequency is 100 hertz, what is its wavelength? Okay, so now here they actually give us speed and they ask us to solve this equation for the wavelength. In other words, we're solving this equation for lambda here. Lambda stands for wavelength. So we know our speed is 50. We know our frequency is 100. Plugging everything in, we can easily solve this equation here for lambda. We got to get lambda by itself because lambda represents the wavelength. Now to do that, we're just going to divide this side of the equation by 100. Whatever to one side, I have to put to the other. So 50 divided by 100 gives me 0.5 meters. Of course, your units are meters because we're dealing with wave length. Okay. All right. You know what? I have a few more speed problems that I'm going to do with you guys. I'm just going to do 3 more. There's some additional problems that I have. Some additional speed calculations that I have in Schoology. I'm just going to do those 3, and then we're going to call it a day. So let me go ahead and pull up that commie file. So we're just going to do these 3 problems. I'm going to call it a day. If a wave has a period of 20 seconds and a wavelength of 10 meters, what is its speed? Okay, so we already know that the equation for speed is equal to wavelength times frequency. Now, notice, guys, we're not given the frequency here. We're actually given the period. But, guys, we all know how to find frequency. We know the period. Remember, frequency is equal to 1 divided by the period. So if our period here is 20 seconds, so what is 1 divided by 20? Well, 1 divided by 20, that's easy. If you put it in your calculator, you will get a frequency of 0.05 hertz. 0.05 hertz. So now that we know our frequency, we can easily find our speed by just multiplying a wavelength of 10 meters times 0.05 hertz. Okay. When I multiply those two, I get 0.5, and of course my units are meters per second. They are meters per second because we are calculating speed. Okay, hopefully that makes sense. So let's do these last 2. Look at this one right here. It says, if a wave has a period of 100 seconds and a wavelength of 250 meters, what is its speed? Okay, so we all know that speed is equal to wavelength times frequency. Again, this symbol right here, lambda, means wavelength. Well, frequency is always 1 divided by the period. My period is 100. If I put 1 divided by 100 in my calculator, I get 0.01 hertz. Once I have my frequency here, I just come over here and plug this in, and I can easily solve this equation for speed. Speed is equal to 250 times 100. I'm sorry, why did I say 250 times 100? Sorry. 250 times 0.01 hertz. When I do that, I get a speed of 2.5 meters per second. Okay. All right, last one. What is the wavelength of a wave that has a frequency of 65 hertz and a speed of 350 meters per second? So here we're solving for wavelengths. Okay, if speed is equal to wavelength times frequency, we know our speed is 350. We're looking for wavelength. In other words, we're looking for lambda. I'm going to plug in 65 for frequency, 65 hertz. And then I'm going to divide both sides by 65. That goes away, whatever the one side I have to do to the other. So if I put 350 divided by 65 in my calculator, what I get 5.38 meters, which is equal to lambda. Again, lambda here, that is a symbol. That is a symbol for wavelength. Wavelength is always measured in meters. All right, any questions on what we did on today? Okay, so the speed equation is really easy. I'm going to go ahead and open up this assignment so you guys can see it. Okay, the assignment has been made open for you guys. Let me stop sharing my screen. If in case any of you guys have not filled out the attendance form, please do so before you leave. Are there any questions before you all head out? Okay, so before y'all leave, I just want to let you guys know that next Monday, it's going to be the last. It's basically going to be the last live Zoom session. The end of the week next week is actually scheduled for final exams. So I will see you guys next Monday. Enjoy your weekend. Bye, guys.